Okay. Good afternoon. I'm delighted to welcome you to the Condensed Matter review session. I'm looking forward to a particularly stimulating and fruitful session. From the list of speakers, I'm confident that we're going to have exactly that. My name is Eitan Grossfeld. I'm part of the physics department here at Ben-Gurion University. We are going to have two review talks today, one experimental, one theoretical. We will start, of course, with the experimental talk. It will be given by Professor Amir Yacoby of Harvard University. Professor Yacoby graduated from the Weizmann Institute. He worked there for many years, but before moving to Harvard a few years ago, his work covers all aspects of condensed matter theory, condensed matter physics, graphene, topological states of matter, spin qubits, quantum wires. In all these subfields, he emerged as a leader and made significant contributions. Today, we'll talk about recent development in the field of topological states of matter, namely how to induce superconductivity on the quantum spin Hall edge state. And I have to say that this talk is sponsored by the American Physical Society. Please.
All right, so I'd like to start by thanking the organizers and specifically Eitan for inviting me to give a talk here. I also want to thank the American Physical Society for sponsoring this talk and the IPS in general for giving me the opportunity to tell you about some of the recent work that we've been doing to explore properties of two-dimensional topological insulators, in particular using superconductivity. The work that I'll be talking about today was carried out by two graduate students, Sean Hart and Hetchen Ren in my group, and in collaboration with the groups of Lawrence Molenkamp at Würzburg, whom we've been collaborating for the past several years on these materials. This is the group that grows our materials for us. And also in collaboration with theoreticians Jason Alisea and Keren Michaeli, some of the last things that I'll be talking about today about some of the implications of topological superconductivity and how it can be detected was done in collaboration with them. So we've heard already this morning an introduction to topological insulators by Moti Segev. The materials I'll be talking about are implementations of two-dimensional topological insulators in the solid state. These are quantum well structures where normally electrons can reside and be confined to move in the plane. These are materials just like any other semiconductor have a band gap. But what's unique is that when you position the Fermi energy in that gap, there exist edge states, and given that this system to begin with is a two-dimensional system, at the edge there resides one-dimensional modes, and these modes carry a conserved quantity. In this particular case, it's a conserved spin current. As you can see here, electrons with one spin orientation are propagating in one direction, and electrons with the other spin orientation are propagating in the other direction. And some of the interest in this field is the emergence of what's called Majorana excitations. These are low-energy excitations that have some interesting properties that I'll just mention. We're not at the stage yet of observing these particles in these systems, but I'll tell you a little bit about how one might be able to create them, and I'm hoping that Adi will tell you a little bit more about their fundamental properties, including their quantum statistics. So how do we actually construct the two-dimensional topological insulators? What are the important ingredients? So I'd like to remind you that starting from the Dirac equation, actually there are several important terms that are needed in order to convert a ordinary two-dimensional system into a topological system. The low velocity expansion of the Dirac equation, of course, produces the Schrödinger equation, but there are additional terms that we very often ignore. These are the mass term, spin orbit term, and Darwin term, and these are crucial in order to generate the type of band structure that is needed for topological insulators. Specifically, if one looks at a particular semiconductor, cadmium telluride, this is a relatively large band gap semiconductor. And if one looks at the orbitals that construct the valence and the conduction band, these are p orbitals for the valence band and s orbitals for the conduction band, you see here color-coded the contribution of these relativistic terms. So, for example, the Darwin term increases a little bit the band gap in cadmium telluride. The mass term renormalizes it again. And spin-orbit interaction leaves the s orbitals unchanged, but of course the p orbitals have an orbital angular momentum, and therefore spin-orbit interaction splits it into two bands. Unlike cadmium telluride, mercury telluride undergoes a much stronger renormalization due to these relativistic corrections. First of all, one notes that the mass term in mercury telluride, which is a much heavier compound, renormalizes the band gap and essentially nearly eliminates it. And once this band gap has removed, now the spin-orbit interaction that splits the valence band is able to invert the bands and produce one of these p-like orbitals to sit above the s orbitals of the which now becomes the valence band. So this band inversion is really important and crucial in order to create the topological nature of these two-dimensional systems. So if one looks at mercury telluride and cadmium telluride, here are the band structures, energy versus momentum. In mercury telluride, as already mentioned, the p orbitals reside above the s orbitals, so it's an inverted structure. And cadmium telluride is more of a conventional semiconductor with s orbitals sitting above p orbitals. Now, normally you'd say, well, this already looks very, very interesting. Mercury telluride has this inverted nature. Maybe in itself will be a topological insulator. But as you can see, it really is only a semi-metal. It doesn't really have an energy gap. One of these bands in the conduction band here disperses downwards. The other one disperses upwards. So overall, there is no band gap in the system. And the way to convert this into an insulator is to position this mercury telluride in a quantum well sandwiched between cadmium telluride barriers. In the limit, when these quantum wells are very, very thin, quantum confinement, which push the s orbitals upwards in energy and the p orbitals downward in energy, restore the original ordering of the bands, giving us back something that looks like a normal semiconductor, resembling very much the band alignment of cadmium telluride. But as one opens up the band, the quantum well more and more, one can restore this inversion, positioning the lowest energy hole-like state, p orbital, above the electron one, and now the bands are inverted only in this two-dimensional system, and this is what's responsible for generating the existence of topological edge states at the boundary. So as a function of thickness, one can see that as the width of this quantum well increases, starting from a narrow well, less than 6.3 nanometers, the system has a band gap, but it's a small gap, and the orbitals, p orbitals, sit below the s orbitals, being a normal insulator. There is a critical width of this quantum well in which the gap closes, 6.3 nanometers in these systems, and then the dispersion becomes relativistic, Dirac-like. And for quantum well widths above 6.3 nanometers, one finds an inverted band gap. So again, a gap opens, but now p orbitals, the red-like orbitals here, sit above the blue ones. In the energy diagram, you see that for quantum well widths less than 6.3 nanometers, there is a gap, but it's the normal gap, electrons sitting above holes. This is the critical width where the band closes, and for anywhere else above 6.3 nanometers, the system becomes a topological insulator, giving rise to a gap in the bulk, but helical edge states carrying chiral spin currents at the boundaries. So normally, if we take one of these systems and position our Fermi energy in the conduction band, this is a system that has very strong spin-orbit interaction, but nonetheless, current is expected to flow uniformly across this structure from one contact to the other. If, however, we can tune the Fermi energy through the system using, for example, a local gate, one can then deplete the system in this gated region, positioning the Fermi energy in the gap, such that now only edge currents can flow. And this is what's known as the quantum spin Hall regime. It's quantum because there is a quantized current and a quantized spin current that will flow at the edges. To give you an indication of where these kind of exciting excitations can emerge in this system, one needs to then create a gap these edge modes, these helical edge modes, in two independent ways. The first one is to generate a gap in the system using proximity effect by coupling this system to a superconductor. This gaps these helical edge states and creates something that is known as a topological superconductor, and towards the end I'll indicate some of the implications of this topological superconductivity in contrast to a normal superconductor. This is one mechanism for gapping. The other mechanism for gapping is to apply a magnetic field in the system. This breaks time reversal symmetry, and this magnetic field will then open a gap of different nature. And it turns out that at the junction between the proximitized gap and the broken time reversal symmetry gap, new excitations emerge, zero energy excitations. These always appear in pairs, and these are known as Majorana excitations. And one of the remarkable properties of these excitations is that they're predicted to have what's known as non-abelian statistics. When you exchange two of them, you undergo a transition to a different quantum mechanical state, unlike fermions and bosons, where you just acquire a certain phase as you exchange particles. And I hope that Adi will say a little bit more about the interesting non-abelian properties of Majorana excitations. But this is roughly the last time that I'll be mentioning them in this talk. Yeah? Here, well, there are, in fact, so at the boundary of this superconductor with this topological insulator, these helical edge states do, in fact. So this topological superconductor here exists all around, if you like, this perimeter.
The magnetic field does not destroy the two direction and introduce helical state, chiral state instead of helical.
No. So in this system, when the magnetic field is applied, first of all, it's applied in a way that does not couple orbitally to this system. So it's applied in the plane. So it only couples to the spin. And so the orbital nature of these states do not change. What is affected is their spin. And now the spin wants to be quantized in a direction that's more parallel to the external field, and that leads to backscattering between the forward moving direction and the backward moving direction, and that's the thing that breaks the this Kramers pair. So what are some of the consequences of this quantum spin Hall effect, the presence of these helical edge modes? So the first thing to note is that, as I mentioned, it carries a quantized current, and it's actually quite, in principle, easy to observe these currents. If you create a system that has multiple contacts, you can envision each pair of these contacts to be connected by a forward-moving and a backward-moving edge state. And so, in principle, it's easy to show that this system is equivalent to a network of quantum resistors, each segment connecting two ohmic contacts here to reservoirs by a quantum resistance given by h over e squared. And so this is the resulting network, and if one just analyzes how current and voltage develops on this system, one can very easily convince oneself, for example, that if one sends a current that splits equally between the upper and lower branch, the voltage that you would measure on the top branch here is going to give you an effective conductance given by the total current divided by the measured voltage given by 2e squared over h. And this is something that has been seen originally in the group of Lorentz-Molenkamp. We have repeated these experiments on systems that have multiple segments of these edges to see how robust is this quantization. And when you look, for example, at a sample after you've explored what the individual resistances of each segment connecting two ohmic contacts, you see that it's hovering close to the quantum of resistance, h over e squared, which is 25 kiloohms, but typically it's larger, sometimes very, very large. And the reason I'm emphasizing this is that, first of all, if there was some mechanism of flow through the bulk that would shunt these edge currents, this would actually produce lower resistance or higher conductance, something that we do not see typically. And in order to generate a resistance or a conductance that's different from the quantum one, in particular one that is a larger resistance, one needs to have something that scatters the edge. This forward-moving edge mode needs to somehow scatter to a backwards-moving edge, and that, of course, requires in some form breaking of time reversal symmetry that we have not induced deliberately into the system. So I just want to point out that this is really an open puzzle in the field right now. It is not understood why the resistance of this system is close to be quantized, but it's not really very precisely quantized, in particular producing a larger resistance than one would expect. But the other implication of this topological state is that, as I mentioned earlier, if you were to go from a situation where the Fermi energy lies in the conduction band, let's say, current is flowing uniformly, once you deplete it, the current should be flowing at the edge. And what I'd like to show is that superconductivity is an extremely interesting and useful tool to explore this current flow patterns in the system, and as well as important in taking a step closer to generating these Majorana excitations. So just a brief review about Josephson junctions. What we envision here is a situation where there are two contacts to this quantum well, two superconducting contacts connected by a normal metal. There is no superconductivity present. There is no pairing present inside this middle region here. And superconductivity is mediated by pairs that are propagating through the sample. What we know about Josephson junctions is that if we were to consider current flow between one contact and the other as represented by these arrows, each one of these arrows can represent a Josephson junction, one junction, which means that there is basically a critical current, supercurrent, that can flow between the contacts and the other along this current path. And it turns out that the relation between the critical current that flows within one of these junctions and the superconducting phase difference between the two contacts is given by the Josephson relation here. Critical current is given by some constant J0 times sine phi. In the presence of many of these Josephson junctions, as you see here, there are many, many ways in which current can flow from one contact to the other, and we're envisioning roughly current flowing along straight lines here. One needs to integrate what the total current, supercurrent, will be in the system, and this is just the integral of this Josephson relation, now being modulated by an external magnetic field that threads some flux. So in the presence of a very weak magnetic field, there is an Aharonov-Bohm effect that basically changes the phase relation between one contact and the other, and that, of course, depends on how far you are from the edge of the sample. And this phase that you accumulate is just given by the magnetic field times the area enclosed by this particular path. And so the net critical current flowing between these two contacts is given by this integral here, that is then proportional to the integral of the current as a function of position, j of x, times a sine function. And what you see is that the critical current essentially is a sine transform, Fourier transform of the current flow pattern in the system. And this relationship, this Fourier transform, is what we'd like to use in order to determine what this current flow pattern is based on the measured of the critical current. Just a few steps can easily show that the maximum critical current, and what happens is when you impose a critical current through this system, it affects the phase difference between the contacts in order to allow this critical current to flow. The maximum one, the one is that the system can no longer sustain beyond that critical current, can be shown to be given by the absolute value of the Fourier transform of the current distribution j of x. So if the complex Fourier transform j of x is given by g of beta, where beta is just proportional to the external magnetic field, the measured critical current as a function of this magnetic field is given by the absolute value of the Fourier transform. And here I've plotted just two limiting cases. I'm sure you're familiar with these two limiting cases. One where current is flowing uniformly. We then know that the Fourier transform of a square function is just the sine x over x, and that's the current flow pattern that we would expect. In the limit where current is only flowing at the edges, because this is a topological insulator, we expect the Fourier transform of 2 delta function, and that is given by a cosine. Here, this cosine has been truncated by assuming that these edge states have a finite width. I want to comment that so far I've assumed that the current distribution is symmetric, but in fact if the current distribution were to be a little bit asymmetric, and there's no reason why we should expect it to be symmetric in a real experiment, that will tend to lift some of these nodes, and I'm not going to talk too much about that except maybe towards the end. Lifted nodes can be understood in terms of an asymmetry in the current flow pattern, but can also be interpreted in a more interesting way that I'll mention towards the end. The problem here is we're interested in the current distribution, so we would like to take the inverse Fourier transform of this function, and the problem, of course, is that we're measuring an absolute value of a Fourier transform, so we're losing the phase. So we have a phase problem. This is a problem known in many, many areas of scattering experiment where you want to construct the underlying function from an absolute value of a Fourier transform. This is something that in the context of superconductivity and Josephson junctions was in fact investigated and solved in 1971 by Dines and Fulton, and they showed very rigorously that with minimal assumptions one can actually, by knowing what the absolute value of the Fourier transform, one can construct the phase using something that's called the Hilbert transform. It turns out that implementing Hilbert transforms are quite hard. They're extremely sensitive to this node here, this 0. But it turns out that you can play some tricks to reconstruct the phase without using the Hilbert transform that I'm not going to mention just due to lack of time. But I'll tell you that there are several different techniques that we can really construct the full underlying current distribution from the absolute value of the Fourier transform. So now let me describe in greater detail the experimental setup. So this is this quantum well that I mentioned before, and we now put two superconducting contacts on top of it, and we can look at the current, the supercurrent through this system. And indeed, one can see a very nice and strong critical current in the range of a few hundred nanoamps. This is in the regime where current is now flowing uniformly through the bulk of the system. We haven't tuned it into the gap. And indeed, if you look at the critical current, zero resistance, which are these black regions here, as a function of the external magnetic field, you very nicely see a Fraunhofer pattern, which drops really, really fast. The central lobe here has twice the width of any other lobe, as you would expect for a sine x over x function. And if you analyze the period here, which should tell you something about the area enclosed by one flux quanta, you conclude that the area is bigger than the actual area of the junction. And this is not unexpected, simply because these are superconducting contacts, and when you apply a magnetic field, they repel the flux. And so what happens into this junction, you apply a uniform field, this junction sees the external field according to this area, but it also traps half of the flux that was repelled by this contact and half the flux repelled by this contact. So the overall net area that we're deducing corresponds to the width of the junction plus twice half of each contact. And this is very consistent with our data.
Why is it non-symmetric?
Non-symmetric has to do with hysteresis. If you were to scan the other direction, you would find this peak being bigger, and it has to do with trapped flux in the superconductors. In order to look at this current distribution now, as a function of density, as we tune the system into the gap, we deposit a metal gate on top of the system, and now we can tune its density continuously. Here you can see the resistance in the normal state of this system, showing that indeed it wants to approach half the quantized conductance, which is what you'd expect for the quantum spin Hall effect. Here, in fact, conductance is higher, or resistance is lower than the quantized value. And we do believe that we have contribution of flowing a little bit of current still through the bulk because the dimensions are now narrow. And the reason we have a narrow junction is because superconductivity decays very rapidly as it extends itself into a normal region, and so we'd like to be able to not lose it entirely. Here are two extreme cases now when we tune the density in the system, one to be in the conduction band, as I've shown before, and one when we've tuned it to be in the gap. And what you can see is that we now know how to transform this Fraunhofer pattern into a current distribution. So this is the extracted real space current distribution, indeed showing roughly a uniform current flow through the bulk of the sample. But once we deplete the bulk, we see that we're left only with current flowing at the boundaries. And the transition is very, very clear. This looks more like a cosine function, again, that's truncated versus something that looks like a sine x over x. And we can now continuously follow the emergence of these edge states as we tune the Fermi energy continuously. This is a non-normalized Fraunhofer pattern, so each one of these cuts is the superconducting critical current versus flux as a function of density. This is the computed current flow distribution, and if we normalize it, one can very clearly see how the bulk diminishes and the edge states remain. You can also very clearly see that this central lobe that has twice the flux quanta narrows down to have only one flux quanta, as you would expect for a Fourier transform of two delta functions versus the Fourier transform of a step function. Okay. So here are some of the widths. We can see this behavior on different samples. Here is a separate sample that we can perform the same experiment. Again, the bulk diminishes, leading to these edge states. And you note that the width that we extract for these edge states is not universal. And maybe in the remaining time, let me just say a few words about the origin. Before that, I want to point out maybe the most important test is to now reduce the width of this quantum well to have dimensions that are below the critical dimension where we know this system should not be topological. And in this case, you can clearly see that these edge states do not exist and the current distribution remains uniform throughout the entire density range. So a few words about the width of the edge states and about some of the nature of these topological edge states. So concerning the edge states, we know that as we move the Fermi energy from the bulk into the gap, the edge states become more and more localized. And so depending on where this Fermi energy lies, we may expect the breadth or the width of these edge modes to depend on that. I already mentioned that the lifted nodes could be interpreted in terms of an asymmetry across the sample, but together with Jason Alisea and Keren Michaeli, we have possibly a different interpretation that is more exciting, that has to do with the underlying topological nature of this system. And I want to just say maybe in 1.5 minutes to give you an insight into that. So I've already mentioned what the current phase relation of a normal superconductor is, and that was the critical current was related to sine of the phase. It turns out that coupling these helical modes, these specific topological edge states to superconductors, leads to something that's known as a fractional Josephson relation. In fact, the relationship has sine phi over 2 rather than sine phi. And what we clearly see in this experiment is something that's related to sine phi and not sine phi over 2. And the question is how do we restore sine phi even if the system has these topological edge states? In the limit, when we have only these two helical edge states, we have two of these Josephson junctions, and each one can contribute this current phase relation, sine phi over 2. But the interesting thing, and that has to do with these Majorana modes, there are two possible current phase relations that can exist, and that depends on the parity of the system, where the system has an even or an odd number of electrons in it. And so we have many possibilities for forming interference about these two edge states, and they're outlined here. And these divide into two categories. One is plus plus and minus minus, and this can be seen here. This would be the current phase, critical current as function of flux. And the other one corresponds to the plus minus minus plus, and it has a destructive interference that leads to a node at 0. If one now assumes that this parity is not even conserved and just is fluctuating throughout the sample, one can show that one would recover the normal periodicity as is explored in experiment, but two outcomes might emerge. One is lifted nodes, which might be the reason we're seeing lifted nodes. The other is a offset by pi that has to do with a second possibility. And so both these possibilities have the right periodicity, but would be a direct signature of topological superconductivity in these systems. And so we are working to try to see whether the lifted nodes that we're seeing is related to this phenomena of topological superconductivity explained here. So with this, let me just summarize that we've been using superconductivity as a means to extract the underlying current flow patterns in these systems. And of course, the next step is to use superconductivity to induce these Majorana bound states and explore their quantum mechanical and statistical nature. Thank you.
On you can see that that's minus 5 and plus 5. There's a weak sequence there.
Yeah.
Are these also connected with the doubling, the halving of the period that you showed?
No. So halving the period will not produce these peaks. It will actually produce something in the middle.
So where do those come from?
These are artifacts of the fact that the system is truncated and that we're not able to measure superconductivity up to indefinite flux, and we basically are truncating our measurement.
They were more obvious on one of the others.
Yes, exactly. But that's correct. Flat.
If you have a SMS junction where the N part is ballistic, you don't get sine phi. You get
Right.
so there are higher harmonics.
Right.
How does that?
So the question is, if you don't have a ballistic, if you have a ballistic channel, the current phase relation is not just sine phi, but it's a square root of something like 1 minus sine phi. I don't remember exactly. But what couples in, the important thing is the coupling, is the transmission coefficient. So even if you can move ballistically from one side to side, but there is a small transmission probability to coupling into this mode, you restore sine phi. We believe we're in that limit. Our superconductor is not tremendously well coupled to the semiconductor, and so I think that explains why we see sine phi.
Is the spin-hole conductance quantized,
Yes, it should be quantized, yeah.
even if you have spin orbit and spin orbit?
You need the spin orbit. As long as you don't have time reversal symmetry breaking, it should be quantized. Yeah. No.
So do you have an explanation? What is the origin of this 200 nanometer width of the edge that you get from the Induced?
Right. So first of all, there is one theory that I'm aware of that has been doing simulations to extract what is the extent of these bound states, and they extract numbers that are in the range between 50 and 100 nanometers. So our width is clearly beyond that. But remember, here we have assumed that current is flowing in a straight path from one side to the other. Obviously, this is not the case. So first of all, things can meander, and our edges can have a little bit of a fluctuation. Second, this order will position your Fermi energy at different locations along the edge at slightly different energies. And so once you come close to the conduction or valence band, these edge states broaden tremendously. Their minimum dimension is somewhere between 50 and 100, but eventually, as you approach the conduction band, they will merge they will become they will merge with the band. And so this order will, I think, meander and make this edge fluctuate in width. And we're extracting something effective to that edge, and I believe that is the origin, and the lack of universality is due to that. Yeah, in this system, the quantum well is terminated by etching. And the gate extends all the way around beyond that edge, so it extends beyond the boundary.
Okay, we should move on. Let's
Thank you.
Amir Yacoby again. Okay, so it gives me great pleasure to introduce Professor Adi Stern from the Weizmann Institute, who will give the theory review. Professor Stern is well known for his pioneering work on the quantum Hall effect, including the discovery of quantum particles at the quarter of the Coulomb charge. And from the very beginning, he led the theory progress in the field of topological states of matter. It was a personal pleasure to be part of that. Today, he will tell us about the making and breaking of matter.
Thank you. Thank you very much, Eitan. It's a pleasure to speak at the IPS conference, and it's a pleasure to share the session with Amir, in particular in the presence of our joint advisor, Joe. What I'd like to tell you about, I don't know why this appears here, but I'm not going to try to fight it. Amir, do you have the... So what I'd like to tell you about is some theoretical considerations to that on how can we make and how can we break non-abelian states of matter. Now, my plan for the talk is this. First, I'd like to explain a little bit more than Amir did what non-abelian anyons are, why should we care about them, and what they might be good for. Then I'd like to tell you about the two pieces of work that I've been involved in. One is on how we can generate from scratch, if you want, a non-abelian state of matter, and this is work done with Netanel Lidner from the Technion, Erez Berg with my colleague, and Gil Rafael from Caltech. And then what happens to a non-abelian state of matter as we take its dimension and make it narrow and narrow, so that we take it through a transition from 2 dimensions to 1, and this is a work with Ran Sagi, Bert Alperin, and Yuval Oreg, and there's a poster today describing it. So first, what are non-abelian states of matter? Well, non-abelian states of matter are made of a few basic ingredients. First, you need a quantum system. It should live in 2 dimensions. It should have a gapped spectrum. So there's a spectrum of excitations, and there's an energy gap from the ground state to the excited spectrum, and the ground state should be degenerate. But this degeneracy should be very particular. Of course, we know degeneracy in quantum mechanics. Hydrogen atom is the first example we all hear about. But those are degeneracy that come from some local symmetry, in that case rotational symmetry, and are broken when we break the symmetry. The degeneracy we need here is a degeneracy that does not depend on detail. It's a topological degeneracy. What I mean by that is that if you look at the Hamiltonian of a non-abelian state of matter, it would look like that. You diagonalize it, at least in as a thought exercise, you diagonalize it. You get a set of ground states which are all degenerate in energy, let's call their energy 0, and an excited spectrum that's gapped. Now you come and you perturb your system by any perturbation you want, any local perturbation you want. You introduce coupling to phonons, you shake the system a little bit, you do whatever you want, and what you find is that there are no matrix elements connecting the ground states. The degeneracy of the ground state is not affected. This is basically what defines a non-abelian state of matter. This is what we need to have if we want to have a non-abelian state of matter. Now, everything else changes. There are changes here, there are changes here, and as a consequence, there's a splitting between the degenerate ground states. But the splitting should be exponentially small in something. It's usually exponentially small in some distances, but it should be exponentially small. This is the defining property of a non-abelian state of matter. Now, if all the ground states are degenerate, how do you introduce dynamics into the system? Usually dynamics is introduced by phases that go like the energy differences time. To introduce dynamics into a non-abelian state, what you need to do is you need to change parameters in the Hamiltonian. You need to change adiabatically parameters in the Hamiltonian. The Hamiltonian has many ground states, and as you change the parameters, the ground state change. Now, if you carry out a cyclic change of parameters, you get back at the end. If you do it adiabatically, you get back to a ground state, not necessarily the original one. So, and I hope you can manage the exercise of reading through the Microsoft symbols. But in any case, what it tells you, what's written here behind tells you, is that an interchange of or a cyclic evolution of these parameters corresponds to a unitary transformation that acts within the subspace of ground states. Now, this unitary transformation, it turns out, for non-abelian states of matter, depends only on the topology of the trajectory. So if you change your parameters in some parameter space in a cyclic way that looks like that, or in something that's less stable, but starts and ends at the same point, you get the same final state. So there's some robustness that comes out of topological considerations. Only the topology of the trajectory changes. Now, this is more or less the definition of a non-abelian state of matter. Why is it good? What is it good for? Well, it very strongly correlates with an idea called topological quantum computation, which is an idea of how to create computers in which when you put PowerPoint, this will not appear. Now, this is an idea I will not get into, but if you have non-abelian states of matter and if you can control and manipulate them ably, then you get a topological quantum computation. But on top of that, I'd like to emphasize, this is also a very interesting basic science question. How can you create a system that's so insensitive to details, where ground state degeneracy doesn't split when you change the parameters? Now, we have some examples for that. We have Majorana fermion that Amir discussed a little bit. We have some quantum Hall states, usually going under the name of Reed-Rezai or Moore-Reed ground states, and we have some experimental progress in the attempts to study Majorana fermions. I will not cover any of this just for lack of time. What I would like to do today is to explain how can we create a topologically protected ground state degeneracy. So I'd like to focus on this issue of a ground state degeneracy that doesn't change as we change parameters. And second, so this will be the first half of the time I have left. Luckily, it doesn't show the clock here. The first half and the second half will be what happens to this protected ground state degeneracy as we remove the protection by making the system narrower and narrower. So the first half, as I said, is done together with Netanel, Erez, and Gil. And there are some related works with less Israeli names, Barkeshli and Chi, Clark, Stengen, and Alishia, Meng, and Vaezi. All of them worked on similar stories. And the starting point is the quantum Hall effect. Now, the starting point of the quantum Hall effect is the classical Hall effect. You know, 2 dimensions, magnetic field, perpendicular to the 2 dimensions, current is flowing, Hall effect, voltage is generated on the 2 perpendicular to the current, and classically we get, as we learned actually as I learned in high school, not too far from here, we get a Hall resistivity that's linear in magnetic field. Quantum mechanically, we get the steps, and the steps are the quantized Hall states. Now, these quantized Hall states have some properties, have many properties, but out of these properties, there are very few that you need to remember if you never heard of them for this talk. One is that this is a system that's gapped in the bulk, like the one Amir was discussing. Second, it's gapped in the bulk, but like the system Amir discussed, it has edge states. But the edge states in the quantum Hall effect are chiral. They move in one direction only. Here on this edge, they move to the right. On this edge, they move to the left. As a consequence of this, the Hall conductivity is quantized. And in the case I'd like to talk about, it's quantized to 1/3 of E² over H. And the last property I'd like to remind you of, and maybe the most spectacular one of this type of quantum Hall effect, called the fractional quantum Hall effect, where this quantity is a fraction, is the existence of fractionally charged quasi-particle excitations. What do I mean by that? What do I mean by that for the context of this talk is that if you look at this type of a geometry, where we have an annulus with one edge at the exterior and another edge at the interior, the total charge on each of the two edges is quantized not in units of the electron, but in units of 1/3 of the electron. Of course, the sum of the charge here plus the charge here should be overall an integer. We can't break electrons. But each one of them can be quantized to 1/3 of an electron. The bulk, by the way, is dead. It's gapped. It cannot be changed. So this was a quantum Hall primer, what you need to keep in mind for the rest of what I'd like to talk about. Now, since I talked for like half a minute about the one annulus geometry, I'd like now to look at two annuli, an annulus above another one. So here we have a green annulus and a red annulus, and each one of them is in a magnetic field, a perpendicular magnetic field. But what I'd like to think about is a situation where the density on the upper annulus is equal in magnitude but opposite in sign to the density in the lower annulus. So these are electrons, these are holes, equal density, equal filling factor of nu equals 1/3, as we said before. And of course a magnetic field, and just keeping or having graphene in mind, we think about the spin being opposite in the two annuli. So as a consequence of having a fractional quantum Hall effect in each of the two layers, by the way, I think about the two layers as being isolated from one another with no tunneling in the bulk. So for those of you who know about graphene double layers and bilayers, this is like a double layer with an insulator in between. So no tunneling in the bulk. Now, so there will be two edge modes, one flowing clockwise, and the other one flowing counterclockwise at the exterior, and two opposite modes at the interior. Now, what I'd like to, what I'm telling you now is a recipe of creating a non-abelian defect of the Majorana fermion type, but somewhat more, somewhat richer. So I'd like to tell you basically a cooking recipe for creating a non-abelian state of matter from a quantum Hall state. And the reason I'm telling you this is I'd like to focus your attention on the crucial relation between the fractional charge and creating something non-abelian. So what I'd like to do now is to connect, to glue or to stitch the two annuli to one another in such a way that basically I create effectively a torus, right? And those of you who know the quantum Hall field know that a fractional quantum Hall state on a torus has a topologically protected ground state degeneracy. Now the problem is this is a theoretical construct. We cannot create a fractional quantum Hall state on a torus because to create a torus with a magnetic field that points outwards from the surface of the torus, we need monopoles. And we don't have monopoles because our high energy colleagues did not supply us with them. I'm saying that because I see Kobe here. This is kind of a poor man's way of creating a torus. We take two annuli and we stitch them together. Now, what do I mean by stitching together? Just since I'm not going to manage these graphics with the circles, let's just take this edge and look at it as if it was straight. What we're going to do, the stitching or the gluing process, is to allow for tunneling between the two layers, between the two edge modes. Now, this tunneling, of course, makes the charge on the two modes uncertain because it allows for electrons to jump from one to the other. Only at the edge. As I said, in the bulk, we don't allow it, only at the edge. The total charge is, of course, 0, just for charge neutrality. But here we have a situation where we have basically two metals this edge state is like a metal, this edge state is like a metal, and we allow tunneling between them. As a consequence, what we get is a wave function that's a sum of many, many values of Q. But there's one thing that cannot be changed by this tunneling process, and this is the fractional part of the charge. Because the tunneling process tunnels electrons. So if we tunnel, if we had a 5 1/3, minus 5 1/3, and we tunnel one electron, we will end up with 4 1/3, minus 4 1/3. I have more examples. The fractional part of the charge is conserved in this process. And we're going to have three different, what's known as topological sectors, but basically three different states with three different values of the fractional part. It can be either 0 or 1/3 or 2/3. Now, the energy does not depend on this fractional charge. And why that? The reason for that is that this wave function will have a very large range of a very large uncertainty in the number of, in the charge. Or if I draw the charge as or the wave function, the probability to find a particular value of the charge, the stronger is the tunneling, the wider spread this wave function will be. And if it spreads over a range of a million electrons, plus or minus 1/3 will not make a difference. And therefore, the energy does not depend on that fractional charge. So we have three different states. They are different, they are orthogonal to one another because they have three different values of the fractional part of the charge, but they are degenerate in energy. The Hamiltonian, this talk is not technical, but the Hamiltonian, if you're interested, has a charging part, which is basically goes like the charge, this Q squared, and a tunneling part, which turns out to go like cosine 6 phi, and the degeneracy can be seen if you remind yourself that the cosine here now has several degenerate minima. So we have three degenerate ground states, and the degeneracy cannot be split unless you change the fractional part of the charge, which means in this annuli geometry, if you want to bring a fractional charge, you need to bring it from the other edge. And if the other edge is very large, it's not going to happen. And therefore, you will have this ground state degeneracy. Now, this gives us a ground state degeneracy, but still doesn't give us non-abelian states of matter, and that's what I'd like to talk about now. Well, here, Amir gave an introduction to what I want to say, and this is the fact that we can gap such edges also by coupling to a superconductor, not just by tunneling, which takes an electron from here and move it to here, but by coupling to a superconductor, which takes an electron from here and an electron from here, forms a Cooper pair and swallow them, or splits a Cooper pair, one electron to each layer. So we now have two ways of gapping the edges, one with a superconductor, in which case, of course, rather than having Q and minus Q, we have a Q and Q. But again, the fractional part doesn't change by splitting or swallowing Cooper pairs. So we can gap by a superconductor, or we can gap by a ferromagnet, which is the tunneling process I described before. It goes under the name of a ferromagnet, mostly for historical reasons. And we're going to have a threefold degeneracy if we have a ferromagnet on the exterior and a ferromagnet on the interior, or again, tunneling and tunneling, or if we have a superconductor at the interior, superconductor at the exterior. But still, that doesn't give us non-abelian states. What will give us non-abelian states is an alternating gapping. If we gap this region by a superconductor, this region by a ferromagnet, or just a tunneling, this region by a superconductor, this region by a ferromagnet, and so on and so forth, what we will have is a situation where there's a ground state degeneracy that scales exponentially with the number of these domino blocks. Okay? This will give us a ground state degeneracy that scales exponentially. And the reason is that now each one of these superconductors, let's say, let me focus on the superconductors, each one of the superconductors can have a fractional charge of its own. And the ground state will be insensitive to the value of that, or the energy will be insensitive to the value of that fractional charge. So altogether, that will give us a degeneracy that scales exponentially with the number of superconducting regions. And I'd like to, and I'll avoid the discussion of when it's 3 and when it's 6. What I'd like to mention is that this degeneracy can be described in terms of zero energy modes, just like the Majorana fermions that exist in quantum spin-Hall effect. Zero energy modes which are localized in between, at the interfaces between the superconductor and the ferromagnet. They are known as fractional Majorana operators or power fermions, but in any case, this is what they are. Those are the localized zero energy modes that will take you from one ground state to another. Now, as I said very early in the beginning, I'm going to focus today on ground state degeneracy and not tell you about topological manipulations and unitary transformation and all that, simply because not only that my time is limited, but it's the pre-lunch talk. So I won't tell you much about this, just that you can calculate the unitary transformation that are being implemented when you interchange these zero modes, and you get a set of transformation that's richer than those of Majorana fermions, but are not rich enough to carry out topological quantum computation, or universal topological quantum computation. And I can expand on that, over lunch break if someone's interested. What I'd like to talk about in the remainder of my time is what happens as we try to destroy the state that we just created. So we said there was a recipe of creating a non-abelian state of matter. Just the ingredients of the recipe were 2 annuli, 1 electrons, 1 hole, each one of them in a fraction quantum Hall state, and regions of tunneling and regions of superconductivity. That's all we need. So now what will happen if we take this system and go to the limit, explore what are the limits of after which this topological protection disappears. So this, as I said before, this is a work with Yuval. Eran Sela was involved in an earlier part of this work. I'm mostly going to talk about the second part. Eran again, Bert Halperin, and there's a poster this afternoon over lunch break. I'm not sure. And what we'd like to examine is this statement that you hear all the time, that anyons live in 2 dimensions. What happens if we make them live in 1 dimension? So for that, I have to introduce a change in my graphics. I don't know how to, I got tired of doing this. So from now on, I'll do my drawings in a top view. So you see these are the 2 layers, the 2 layers, and here are the gapping. This is, what was it? Ferromagnet, superconductor, and this is what used to be the annulus. So this closes like that, and it's now a thin annulus. In fact, it's a thin annulus, but it gets even thinner. Here it is now. It's very, very thin. It's almost 1D. Do we lose the non-abelian defect that we just talked about creating? The question I have to say comes up or is sharpened by the fact that we know that Majorana fermions can live on wires, can live in 1-dimensional system with no problem. In fact, they, in some sense, feel more natural in 1 dimension. So can we get this? Can we get these fractional Majorana fermions to live in 1 dimension too? The answer is supposed to be no, because there's a theorem that says that it shouldn't be allowed, and this is in two different works by Ari Turner and collaborators. Erez Berg is one of them, and Frank Polman is the other, and Fidkovsky and Kitaev. So if they tell us it's a theorem, let's see how it works. Shalosh? Okay, tada. Let's see how the theorem will work. As always, it's nice to try and break the law and see what happens. So to do that, I get back to my original system. The two annuli fully gapped by only a superconductor in the interior, only a superconductor in the exterior. Basically, this is a Josephson junction. Let's ask what happens to a Josephson junction. So now we are in a somewhat question that belongs maybe to a different, to a much simpler world. A Josephson junction where the insulating part is made of an electron hole double layer of a fractional quantum Hall state. So of course, if this thing was very wide, there would be no tunneling from edge to edge, and the fractional part on each of the edges would be conserved. And we talked about that. This fractional part can be 0, 1/3, or 2/3, and it should be opposite here and here because the total number of electrons is an integer. But and the Hamiltonian would look like that because the states are all degenerate. But now, as we make it thinner and thinner, there will be tunneling matrix elements that tunnel charges from the exterior to the interior. And we can calculate the effect of this tunneling matrix element. It basically boils down to diagonalizing a 3x3 matrix. And we are 4 people, so we managed. And what we find is, okay, now, it makes sense to ask the question number 1 that you ask about the Josephson junction. How does the spectrum look as a function of the phase difference between the two superconductors? So here's the energy as a function of phase difference, and it turns out, and here I'm not talking, I'm not yet, I will in my last minute, talk about the question of what happens to non-abelian anyons as we shrink to one dimension and so on. But as a primer to this, what we see, something interesting about this Josephson junction. We see that it has, this Josephson effect is 6π periodic rather than 2π periodic, and that there are degeneracy points which remain at particular values of the phase difference. Which is to say, we started from a system, the two-dimensional system had topological ground state degeneracy. All the 3 states were all degenerate. Now we allow fractional charges to tunnel from the interior to the exterior. We split this degeneracy, but we do not fully split it. Something is still left behind. Even in the limit of 1 dimension, something is still left behind. So can we make non-abelian anyons of that? Well, the answer is no, as the theorem tells us. And the way to see that is this. Remember, this black, now I'm coming back to this full-fledged geometry with superconductors and ferromagnet and so on. What turns out, and I won't get into details on that, what turns out to destroy this non-abelian fractionalized Majorana fermions in the limit of 1 dimension is the fact that even though I can keep them very far away from one another, I can keep the interfaces, the 0 modes, very far away from one another and still be in the 1-dimensional limit. But superconductors can talk to one another through Josephson tunneling, and this Josephson tunneling turns out to destroy the fractional Majorana fermions and leave us with only Majorana fermions. So in 1 dimension, indeed, it's only Majorana fermions that whose ground state degeneracy is protected. So to summarize, let me say one sentence about, in some sense, the motivation behind these works. What I really would like to be able to say is to fill this dotted line. What I would like to get to a level of understanding of this issue of non-abelian states of matter, of ground state degeneracies which are topologically protected, to a level of understanding that corresponds, to the level that we understand Bloch bands or band insulators, something like that. So we'd like to know, what does it take for an electronic system to form a fractionalized state or a non-abelian state? We don't even know to say what it takes to form a fractional quantum Hall effect. We just know it's observed in the lab. So this is what I'd like to be able to fill. For the time being, what I told you is how to implant non-abelian defects into an abelian quantum Hall state, and what survives and what doesn't survive in the transition to one dimension. Thank you very much.
Thank you for the talk. Any questions?
Just for curiosity, what happens if you take a disk and act an annulus?
If you take a disk and you stitch it alternatingly, superconductor ferromagnets, black, yellow, you get a topological ground state degeneracy, you get everything. You cannot go to the 1D limit, because the 1D limit I went by making the annulus thinner and thinner. But other than that, the annulus was needed for the second part of the talk, not for the first. You get the same ground state degeneracy. Again?
Topological insulators, you need time versus symmetry. Here, you imagine somehow putting a magnetic field so that it will have an opposite effect in the two layers, but still preserve overall time versus symmetry. Do you have an idea experimentally?
Yeah, no, you don't need to keep time versus symmetry. No way. It's, there's a magnetic field. What takes the place of time versus symmetry here is particle-Hall symmetry, because you have electrons and holes of equal density, basically equal low energy physics. So this is how you compensate for breaking time versus symmetry. In fact, you may know that in graphene you can see topological insulator physics in like 25 Tesla or something, because of particle-Hall symmetry, basically. What?
Regarding the realization of this system, we talked about graphene, but what about double electron hole double wave?
In let's say, gallium arsenide. Yeah. So I should say at some point, and since I didn't say it till now, I'm sure you realized it, but I should say it at some point. This is very difficult experimentally. From the slide with my name and the funding agencies to the slide of the summary, it's all very difficult experimentally. Now, so in gallium arsenide, one of the difficulties is inducing superconductivity. That wasn't, to the best of my knowledge, correct me if I'm wrong, that was never done. Right. But, I mean, we'll do it, and then we can.
Okay, so.
Thank you very much. מי זה שלך?